The Ballast Water Management (BWM) Convention aims to protect the environment from the potentially harmful effects of ballast water discharges. This film will raise your awareness of why the BWM Convention is needed, help you become familiar with its requirements, and show how a ballast water management plan can be developed. As we have just seen, ballast water can have a major impact on our environment. To prevent this from happening in the future, it is important that we comply with the requirements for ballast water management. Globally, it has been estimated that approximately 3,000 to 4,000 million tons of untreated ballast water are discharged every year. It has also been estimated that ship ballast transports more than 10,000 species. This includes living organisms and pathogens such as bacteria and viruses, which are discharged with the ballast water when the ships reach their destination. Many species of bacteria, plants and animals can survive in the ballast water and sediments carried in ships, even after several months. Anything that is small enough to pass through the ship's ballast water sea chest, strainers and pumps may be carried in the ship's ballast water. There are thousands of marine species that may pass into the ship when it takes ballast water on board. Many of these creatures can use the sediment, which is taken on board along with the ballast water, as a refuge. Foreign species are not only transported within the ship's ballast tanks, but also attached to the propellers, the outside of the hull, inside the sea chests, or on other parts. Invasive organisms may also be introduced through biofouling of oil rigs and their support vessels. The rigs often remain anchored in one area for extended periods of time and can become colonized like an artificial reef before being moved to a new site. However, It has been calculated that the most likely distance for maximum invasive colonization is about 8,000 to 10,000 kilometers between native and non-native site. Marine species have always been spread throughout the ocean by natural means, carried on currents and attached to floating wreckage, even before ships started to carry water as ballast. The natural barriers of land masses, ocean temperatures, salinity and depth have created the ecosystems we see in the oceans today. A pan-global tropical zone separates the northern and southern temperature and cold water zones. This allows many species to evolve independently and results in a different marine biodiversity between the north and the south. However, rapidly increasing world trade and the use of larger and faster ships, completing their voyages in shorter time, has reduced many of the natural barriers to the spread of species across the oceans. Many factors affect the likelihood of invasion and establishment of foreign species due to ballast water. Ports where large volume shipments of bulk cargoes take place can be vulnerable to invasion when combined with other elements. Invasion hotspots of foreign species have a high density of marine traffic, but not all areas with high shipping density are hotspots. Factors like environmental similarity and the length of the transport also affect the likelihood of invasion. Marine species have life cycles that include a planktonic stage. Plankton is the name of the microscopic organisms that float freely in organic currents and other bodies of water. Tiny plants are called phytoplankton, and tiny animals are called zooplankton. These tiny organisms, whether plant or animal, are the first link in the marine food chain, since they are a food source for many animals. Plankton comes from the Greek word planktos, which means drifting. Certain species may be transferred in ballast water during their non-adult phase. The adults are unlikely to be taken in as ballast because they are too large, live attached to the seabed, or are in a different environment for part of their life cycle. If there is a high starting density of organisms and the voyage is short, there is an increased chance that there will be surviving organisms in the tank at the end of the voyage. The maximum length of survival of organisms in ballast water varies and is often unknown. In general, ballast water must have been within a ship's tank for 100 days or more before the risk of survival of the species is reduced to an acceptable level. Rising global temperatures could lead to an increase in foreign species invasion. Changing environmental conditions, for example in areas that were previously dissimilar, are now more likely to support the same organisms. Changes in trading patterns, for example by opening the Arctic trade routes for more traffic, causes a shift in shipping intensity. Opening up new areas could lead to a spread of potential new species. Most of these species do not survive the journey or survive in new areas, but occasionally some do. If aggressive and fast reproducing, an introduced new species may not have the same natural break, such as pathogens, grazers, predators or parasites, on its population numbers that it had when in its native environment. The introduction of new species can therefore often expand unhindered and have large and harmful consequences on the new host ecosystem. We have now learned about the history of ballast water and the different threats it poses to the environment. Now let's take a look at an example from real life. The invasion of the Black Sea by a voracious comb jellyfish from North America is one of the best documented examples of a marine alien invasive species introduced through ballast water. The comb jellyfish arrived on ships from the American Atlantic coast in 1982. It eats both zooplankton, the food of commercially important fish in the Black Sea, and the eggs and larvae of the same fish species. With no enemies in their new home, the jellies propagated at an alarming rate. By the mid-1990s, they accounted for 90% of the total biomass in the Black Sea, a biomass more than the total annual fish catch around the world. The species quickly spread into the neighbouring Sea of Azov too. The invasion contributed to the near collapse of Black Sea commercial fisheries within a few years. The once quite prosperous seafood industry has lost about $1 billion since the jellies were released. Anchovy fisheries in the Azov Sea, already under stress from pollution and overfishing, completely collapsed. Dolphin numbers in the Black Sea and Azov Sea also dropped dramatically as the fish they used to feed on disappeared. The entire ecosystem has been disrupted. The jellies have even reduced the amount of oxygen in the Black Sea. They've now entered the Caspian Sea, where they are causing the same problems, and have been found in the Baltic Sea and along the Atlantic coast of Norway too. We have considered the natural spread of marine species, how the spread occurs and barriers to natural spread. And we have considered examples of the ecological and economic consequences of the introduction of invasive species in new ecosystems. The Ballast Water Management Convention entered into force in September 2017. The BWM Convention has three main aims: minimizing the uptake of organisms during ballasting, minimizing the build-up of sediments in ballast tanks, which may harbor organisms, and undertaking ballast water management measures, including ballast exchange at sea, to minimize the transfer of organisms. The Ballast Water Management Convention defines ships very broadly as submersibles, floating craft, floating platforms, floating storage units, floating production, storage and offloading facilities. The Ballast Water Management Convention does not apply to ships not designed to carry ballast water, ships only operating in waters of one party's jurisdiction, ships only operating in waters of one party's jurisdiction and the high seas, warships, naval auxiliary ships or other ships only operated by a state on non-commercial service, and ships with permanent ballast water in sealed tanks. The United States of America has established independent ballast water management regulations. The U.S. Coast Guard USCG regulations entered into force 21st of June 2012, affecting all vessels trading in U.S. territories. The USCG discharge standard is similar to the IMO discharge performance standard D2. This means that a ballast water management system using treatment technology must be installed. On the 2nd of December 2016, the USCG issued the first USCG Ballast Water Management System Type Approval Certificate to the Norwegian manufacturer Optimadin AS. All ships calling at US ports and intended to discharge ballast water must either carry out exchange or treatment, in addition to fouling and sediment management. According to USCG regulations, they also need to clean ballast tanks regularly to remove sediments, rinse anchors and chains when the anchor is retrieved, remove fouling from the hull, piping and tanks on a regular basis, maintain a ballast water management plan that includes the above, in addition to ballast water management, maintain records of ballast and fouling management, and submit a report form 24 hours before calling at a US port. The exchange of ballast water will only be allowed until the implementation deadlines for treatment systems. As the first USCG type approval was not issued until 2nd of December 2016, the USCG extended the deadline for compliance with the treatment standard. This allows ship owners to use an alternate management system and apply for an extension to the compliance date. The possible extension, which was initially 2018, has now been extended to 2022. Those with a granted extension may apply for an additional extension. The BWM Convention is divided into 22 articles and an annex. The annex is an integral part of the convention, meaning that reference to the annex is the same as reference to the convention itself. The headlines for the individual subsections of the annex guide you to the relevant requirements. Sections B and D are of particular importance to ships. The Convention and the Annex call for a number of guidelines to be developed to guide the implementation of the specific articles and regulations. There are 14 guidelines in total, and they are often referred to with the letter G and a number, for example, G2. The process for achieving compliance with the Ballast Water Management Convention can be carried out as a 7-stage process. Some steps may be carried out in parallel. Understand your obligations under the IMO, USCG and local regulations. Do you need to comply with D1 or D2, and when? If your ship is entering a US port and planning to discharge ballast water exchange or treatment must be carried out, in addition to sediment management. The USCG also requires a ballast water management plan, clean ballast tanks free from sediments, and a report which is to be submitted to the US authorities 24 hours before arriving at a US port. Review the current shipboard ballast tank, pumping and piping arrangements. Multi-use of tanks, for example tanks used for ballast and storage of grey and/or black water. Be aware that sampling shall not be carried out during stripping operations due to mixing of drive water with ballast water. Start developing your ballast water management plan at an early stage. It can then be reviewed as your preparations for compliance proceed. Select and install a ballast water treatment system. Selecting and installing a treatment system needs careful consideration and planning. You will need to ensure that plans are submitted to class for approval in good time, and that the system and any ancillary equipment are delivered to the ship on schedule. Further, if you plan to operate in US ports, be aware the USCG has more stringent criteria for ballast water treatment and approval of ballast water treatment systems than those of the IMO. Develop training for ship staff and ensure they are adequately trained in ballast water management operations. A staff training scheme has to be developed and included in the ballast water management plan. Develop a final ballast water management plan and submit for approval. The final version of the ballast water management plan needs to be approved both internally and by the ship's flag administration. Approval is often carried out by a classification society on behalf of an administration. The final stage is survey and certification. When all preparations for compliance are complete, arrange for an initial survey of the ship for issue of an International Ballast Water Management Certificate or Certificate of Compliance. The BWM Convention entered into force in September 2017. From that date onwards, ships may be subject to inspections by port states to determine if they comply with the BWM Convention's requirements. These inspections are limited to verifying certification, inspecting the ballast water record book, and sampling ballast water in accordance with IMO guidelines. In 2014, the IMO adopted guidelines for port state control under the Ballast Water Management Convention. These provide basic guidance for conducting port state control inspections to verify compliance with the requirements of the BWM Convention. They are not intended to limit the rights the port state has in verifying compliance with the BWM Convention. As part of the inspection process, Port State Control has to find out if the ballast water contains harmful aquatic organisms. The procedure is a 4-stage inspection. Stage 1. Initial inspection to check that ballast water management plan is met. Stage 2. A more detailed inspection to check the operation of ballast water management system. Stage 3. Sampling. Stage 4. Detailed analysis and samples to verify compliance with the D2 performance standard. We have now reached the end of the second chapter. We have had an overview of the Convention and the Annex and learned where to find the applicable regulations. We have considered the regulations for control and enforcement of the Convention. Finally, we have had a brief look at the more stringent requirements of the USCG on ballast water management.